In this interactive training video, you will learn some basic principles regarding geometry cleanup. Please keep in mind that the video is designed to help Hypermesh beginners to get started. Later on, while employing Hypermesh for your studies, you will see that there are actually many other ways to clean up the geometry. And now, let's get started. What is geometry cleanup and why do we need it? This question can be best answered by running a demo. As this is just an introductory video, the demo model will be a basic example. Nevertheless, the cleanup operations shown will help you understand the principles of geometry. Let's import the Hypermesh model, named Demo. Just click the highlight. Note, as it is a Hypermesh model, we need to choose Import Model. Import Solver Deck refers to a given finite element model, such as a radius, an ANSYS or an abacus model. Import Geometry is about CAD data import. Import Connectors is about welding information. The next steps should be straightforward. Take note. After importing a model, you may not be able to see it right away. You might think that clicking on the Import button again will help. However, this will just import the model multiple times. In the event that you do not see your model after importing it, try clicking on the yellow highlighted icon, which is normally helpful in this situation. To better understand what the model is, it is helpful to rotate and shade its surface. In this case, you don't need to click anywhere. The rotation is already recorded. Now, we are opening up the model browser. In the first instance, the model browser provides an overview regarding the model contents. As you will see, the model browser is very fundamental to many modeling operations. Simply click on the geometry icon next to the component of interest. This will deactivate or activate the geometry contents. Just watch and note what is happening on the screen. The geometry of LVL8 is deactivated. What do you see? What is it? Keep these plus symbols in mind. They indicate so-called line handles. Note, we do not see the outer contour of a surface. This is very basic, but very important, also in regard to the succeeding operations. The lines of component LVL9 are deactivated, whereas the geometry of component LVL8 is activated. Note, there are no line handles displayed. Thus, we are looking at surfaces. Please also note, there are other ways and options to understand the content of the components. For instance, you may simply count the entities contained in the component, or you may activate the so-called Mask by Config browser. The Mask by Config browser allows in a convenient way, for instance, to only display lines. This would be a one-mouse click operation. Alternatively, In order to distinguish between lines and surfaces, you may shade surfaces, which will be shown in the following slides. But first let us activate the geometry of component LVL. Again, note the line handles in the left upper part of the model. There is something else which is at least as interesting. What do we know about the connectivity of the surfaces? Practice will tell you that the surfaces are not necessarily stitched together. However, if surfaces are not stitched together, the finite element mesh will not be either. In other words, the finite elements would not be connected, which is not a good situation for meshing. However, you are modeling contact interfaces, where parts of the model are supposed to slide with respect to. In order to add information about the surface edge connectivity, just activate for instance, by topo. By activating by topo, the surface color turns to gray. Whereas, the edges are colored now. The color is a kind of coding. Green tells you that two surfaces are merged together. In most of the cases, this is what we want to have. Blue edges are also likely, and correspond to suppressed edges. This means that a shared edge is temporarily out of order. The surfaces attached to a blue edge form a larger area now. Then, we may have yellow edges, which indicate that a minimum of 3 edges are merged together. For instance, the common edge of a T connection would be marked yellow. Finally, red edges refer to free surface edges. In this example, the outer contour of the 2D model needs to be red. But what about the red edges inside the model? Is this correct? Let's try another display mode now, namely by mixed. The display mode, by mixed, keeps the edge color and adds the color of the component to the surfaces. Just compare the surface color with the color of component LVLA. Now, let's learn more about the red edges inside the model. Per definition, each free surface edge is marked in red. If the gap between the surfaces is small, it would appear from a distant view that we are facing single red edges inside the model. This may be annoying at the beginning. To solve these annoyances, let us zoom into the mark. Zooming in brings the answer. There are 2 red edges separated by a gap. Keep this in mind as it is very important. Based on the brief topology review, it is obvious that we need to stitch the surfaces together. This is the objective of the next working steps. The toggle command enables us to stitch surfaces together. This is a manual process, as we need to click on each pair of red edges, respectively. The cleanup tolerance, which is automatically determined during the model import, describes the average gap distance between the surfaces. In practice, and as it will be shown later, you often need to increase the cleanup tolerance increment. Notice how the toggle command failed by prompting a gap distance. The value given here is not necessarily the one of the gap. It may reflect the distance to another edge in the vicinity. We increase the tolerance value slightly, and then try the toggle command. What you need to remember is that the toggle command requests you to click on each pair of surface edges in order to change their topology. This gives you perfect control. However, it is a tedious task. In the next step, we learn an alternative way of changing the surface edge topology. We just re-entered the panel from before, but we are now in the subpanel equivalence. The main thing about equivalence is that you can access as many surfaces edges in a single step as you want. In a single shot, most of the red edges are converted into shared edges. Notice how very simple and quick that was. As there are still some red edges left, we can try it again using a somewhat larger cleanup tolerance. We are getting closer to our goal. As a reminder, the goal is to only have green edges inside the model. However, despite the increased cleanup tolerance, there are still red edges left. Of course, we can increase the tolerance once more. But in our case, this will not. Turning off the lines of component LVL9 is the answer to our little problem. Unfortunately, the color of the component LVL9, and thus, the color of its lines are red. This is in fact the cause of the problem that we encountered here. Keep in mind that the color of lines does not say anything about the surface connectivity, as lines are not part